Hello everyone. I will be doing my presentation on ion channels and neural or neural communication and kind of what that entails. So for my introduction, I wanted to break it up into some fun parts. One of them being first thing, what is an ion channel, and a bit what does it do. Not as much what its purpose is, that's a bit later in the presentation, but what is it, kind of what as a basic level does it do? What different types are there? Because it's not just one. Where are they located? Where are they predominantly located, even though they are in all cells? Is there a spot that they are more predominantly at? What is their purpose? I wanted to go into that to kind of see how it actually interacts within the body. How does neural communication work? Kind of the actions. There's two different sets of actions, and kind of how do they work and how do they spread along. And then some associated diseases. I always like when we go into these topics to look up diseases that cause it. It might just be that that's a bit more of what I studied in my undergrad, but I like to look at when things don't go right, what can appear. So first, what are ion channels? Well, the first thing about them, they are membrane proteins that allow ions to go through. As we can see here, I like the structure of how it is. It is with alpha and beta, not beta, gamma conformation, and of course it goes from inside of the cell to outside of the cell. And the main part about ion channels are they're very selective. It's not just anything can go through. It's not just a straightforward opening. They are selective based on size and charge, and that can fall into, of course, the different types of neurotransmitter chemicals, like potassium, sodium, chloride, things like that. Each of them are very distinct of what they allow through in the different ones of those. And then they change in their conformation state. When that ion goes through, whether any of the triggers that cause it to open, it changes shape a little bit, allowing for it to open, as you can see, from open to close to open, to allow things to go through or to allow it not anything, or not that certain thing to go through. And then they're regulated by membrane potential, and we learn about gradients and just different charges. If something is already super positive, it's not going to let a potassium in or sodium in, because those are already positively charged, and it wants to actually get rid of them. So it's going to close in one direction but open in the other, allowing it to go through. Come on. Okay. So there's three predominant superfamilies of ion channels, and they have them here. There's some of them where it's always open, but the main three that I wanted to talk about are your voltage gate channels, i.e., if let's say a sodium is needed from one side and goes to the other, it can pass through based on what the voltage of the gated side tells it to. One of my favorites that I really like is ligand gated, i.e., there needs to be a key, as it has here. The neurotransmitter pops in, attaches, and then allows the sodium to go through. It's basically a key to the gate, allowing the ion to go through. And then there's mechanosensitive ion receptors, or you can see them as mechanically gated, which can be done by trauma or pressure from one side of the cell to the other that can cause that to happen. It is a bit more the physical allowing it to open rather than a chemical or electric charge letting it through. So where are they found? They're found in all cells, but of course they're found on the plasma membrane in those cells. But my main point that I really wanted to get across from this is that they are essential for physiological survival. In all those cells, they're needed. If it's not in there, you cannot keep a good membrane potential in it. You can't keep a good system in there, a good charge. And then they're more densely found in skeletal and muscle cells, which we'll get into later on why that's important that they're there comparative to other ones like skin cells, why there's less ion channels there comparative to cardiac muscles. And then they do allow for quick action. That is a very important part when it comes to, again, with these skeletal and muscle cells. Why do these actions have to be quick? And especially with cardiac, when things are pumping, and they keep on going, why is it important that it is supposed to be quick compared to other proteins that might take a little bit longer comparative to these? Okay, let me actually use that button. That's so much better. So let's go into neural communication. And there's two different groupings that I broke it up into. And the first one is synaptic transmission. So with this one, I didn't know how deeply I wanted to go into it. But I wanted to show primarily, of course, those ion channels and why they are so important to this. So when you're talking about neural communication, neurons talk through action potential, i.e. charges changing rapidly. And you always, whenever you talk about it, you see that chart where it has depolarization up to the threshold, the action potential threshold, and as soon as it hits it, then the ion channels will switch, allowing for it to go back to hyperpolarization, and then it goes into the resting potential just for it to go back up. But the starting part, you've got to look at the synaptic cleft. So I think in the other image on the next slide here, don't read any of that. In here, there's this area in between both of the neurons. And right there is the synapses, and in between theirs is a little space called the synaptic cleft. And it's basically where, of course, one neuron decides to send the message or send the impulse through to the next one. And one of the things that's important is at the presynaptic neuron, at that area of the synaptic cleft, they have vesicles that have these neurotransmitters in them, and these neurotransmitters can be ions, but one of the they are attached by calcium coming through the ion channel, attaching to these vesicles, which forces them to the membrane of the neuron, and they shoot out their neurotransmitters into the cleft. And one of the ones that is very important for pain that I really wanted to bring out was glutamate. Glutamate goes to the receptors on the postsynaptic neuron, and that opens up ion channels, allowing for sodium, potassium, chloride to go through. And when those go through, it, of course, passes on that action potential, changing it to the next one for it to rush down the cell. So, action potential is the second grouping. And one thing that is very important, because you're looking at these neurons, and you have this long stint. We've already gotten through here, or we've gotten through to pass on to here. This part already has the action potential, and it needs to shoot down to go to, of course, the next one. But how does it travel down there? And that's what a big thing about action potential is. Sodium is predominantly outside of the neuron, while potassium is on the inside. Of course, there are some sodiums, but one thing that we do need to look at is potassium channels, sodium channels, and of course the sodium-potassium pump. As sodium enters into the ion channel through the head of the neuron that we talked about in the last slide, it causes these sodium channels to open up. And when they open up, more sodium rushes in. And if you can think about a lot of these, thousands of these, on the line of the axon of this neuron, as it starts here and travels down, more and more enter and more enter, which causes this positive feedback, also known as amplification. It's what allows the signal to be sent across the neuron super quickly. And as it builds up and builds up, it shoots through. And then when that happens at the end of it, when the impulse is then sent on to the next one, this is at the very end, sodium ion channels close. No more is needed. It's at the end. You can't amplify anymore. And with all of this, I wanted to bring up what ion channels do to reset. You're talking about all this happening, and if there was a bunch of sodium still left in the axon, and of course into these dendrite areas, it couldn't do that again because it's already filled with sodium. So what does the axon do, and of course the entire neuron do? To levelize, first it starts by pushing potassium from inside the cell. Let's go back here from where it already is. Outside of the cell, it opens up these channels, allowing potassium out to kind of equal out. And after that happens, after it's all set and everything's done, the sodium-potassium pump decides to reactivate. And at a ratio of 3, I believe it's 3 sodiums to 2 potassiums, they swap places. They go back to where it is, or where it was before, where potassium is inside the cell and sodium is outside of the cell. And this allows for it, of course, yes, to reset so it can start over again. The neurotransmitters reset. The sodium ion channel opens back up, allowing for sodium to go back through, because it was the inactivated gate popped up when the amplification was done with. And of course the cycle resets and we go back, of course, back to the synaptic transmission. And this happens over and over and over, allowing for more signals to go through. If it was a one and done thing, we would have a problem with pain receptors would be really quick. We wouldn't be able to sense things. Muscle contractions would not be continual. And we actually will go into some diseases that show that happening, where pumps or ion channels cannot work properly, and thus muscular contraction and signaling can't be effectively done. So what is the purpose of ion channels? And I was debating on putting this one earlier in the presentation or later, but I wanted people to know what it was before, like what the step does with the neural communication to allow for this to happen. Well, of course, yes, it maintains membrane potential. Because of those ion pumps, we can go back to the neuron when it's reset. It allows for the potassium to come back in and the sodiums to stay out, and have a flow of it that keeps it pretty constant. We're always taught about homeostasis. Well, ion channels are not foreign to homeostasis, and they do try and keep those levels. Of course, they are important for muscle contraction. For those signals to be sent, especially through the muscles and the neurons, to tell your muscles to contract and move and relax and contract, you have to have ion channels for it to tell it that. Nerve impulse control, i.e. signaling, is very important. If you have pain in an area, if you have a wound, healing needs to know where the area is, or even if there is a cut, for white blood cells to come out, platelets and healing factors to come out to help that. How is that done? Through ion channels and signal transduction. And of course, hormone secretion. we know that in times of stress, we need cortisol. Well, for that signaling to go through that, we need cortisol from it to go to the brain, to the HPA axis, and then to the adrenal glands. There has to be signaling all along the way, and not just from hormone to hormone, but actually through signal transduction. So let's talk about a couple diseases that I found interesting. And it was kind of cool because we were talking about mutations in genes earlier this week that then cause problems. And the other ones were for coding and for cell cycle, and these ones are for still coding for stuff for ion channels. The first one is Anderson, it should be Tawil syndrome. I accidentally put Tamil syndrome. I have a hard time with my W's and M's sometimes. But it's a mutation of KCNJ2, whatever that might stand for. But just note that gene is responsible for transcribing, making potassium ion channels. And when those are disrupted, you can't have effective potassium ion channels. The predominant effects are to cardiac and skeletal muscle cells. These cells do not have proper signaling, and especially when it comes back to, in some of these cases, resetting, coming back to baseline in action potential. And so with the muscle aspect of it, it does cause muscle weakness, lethargy. People with this syndrome have a harder time carrying things, have a harder time moving around, and they do get tired very easily muscularly, and it can cause pain in the muscles if overexerted, and it's hard for them, of course, to build up muscle. And another one is cardiac arrhythmia. When I'm a heart nerd, so when it comes to action potential of the heart and pumping, it is very crucial through the SA node and the SV node, or the AV node, and Purkinje fibers and bundle of his, that each of those are going off at the right time. You need effective blood pumping. And with this, it's hard to have the action potential reset or go in the proper rhythm when different areas of the heart might have different disruptions in their potassium ion channels. And then this is the scariest part about this, is it does cause periodic episodes of paralysis. Let me make sure. And these, from what it looks like, these aren't just like, oh, it's a minute or two. These can last hours to days of these episodes, and the time in between these episodes isn't regular. It can be an hour in between each of these day-long episodes, or it could be years between these episodes, depending on how many are affected and what areas of muscles and the brain and each of those are affected. And I always found that scary. It's almost like a caged-in syndrome that just doesn't allow them to truly move in those states. And so people with this syndrome can't drive, they can't do a lot of normal things in case they fall into an episode. And there are some triggers that they have found for this. Don't overexert yourself, don't go crazy, don't they need their sleep, they need good nutrients, don't do too much, is kind of the thing that they stated a lot over. The next one is Becker's myotonia. And of course, this is a mutation, a loss of function mutation. They were very clear about that while researching it, that it wasn't just any standard mutation. It was a loss of function mutation of CLCN1. And these ones affect chloride channels. I wanted to pick two that had different channels with it, one negative, one cation, one anion channels, to see what it does. So the other one, you had a hard time with moving, with getting stuff done, having action potential hit. And this one is a bit different. So the symptoms show up in early life. In Becker myotonia, there's another one called, I believe it's Thompson's or Thomas myotonia, which shows up between ages 1 to 5 in average. This one is between ages 4 to 12 that symptoms can start occurring. So there's a little bit of gap time where everything seems normal, and then symptoms can progress. So this one is a bit different. The other one, yes, it was a bit of inaction or a hard time to get action. This one is a reduced ability to enact. So delayed muscle relaxation. And one of the triggers for this is sudden movements. So people with this condition, they tell, don't stand up quickly, don't move quickly, don't stiffen your muscles, and don't surprise them. Like, don't jump up and spook them, because it can literally freeze them in a tensed up state for a certain amount of time, for depending on the person, from 15 seconds to a couple of minutes. And basically, as soon as they tense up, their muscles have a harder time relaxing and going back to normal, which can be very harmful when someone is, let's say, running around, and especially if they're a younger kid who's just starting to show symptoms of it. They could be running around, tensing their muscles, playing a sport, and then they kind of just collapse into this stiff ball, and it can almost look like a seizure because their arms are shaking because they're so tensed up, and they fall kind of flat, or they fall kind of in that same shape. And it can also be characterized as just a stiffness of muscles. People with this condition, especially those who avoid strong triggers and don't go for the full stiffness, almost like a paralysis in the other direction of just holding still, they will have stiffness of muscles. They'll be walking around and, okay, this, your hamstring's a little tight, or this is that, but it kind of holds on for a second, and again, they almost have to work it out and let it return to normal, because those chloride channels are ineffective, and so it takes a lot longer for them to go back to normal. And again, for this one, it's both of them are about minimizing triggers. With Andersen's-Tawil syndrome, the triggers aren't 100% fully known, but these ones are a bit known, of sudden movement, no scaring them, no exciting them. People with this condition, I shouldn't say them, people with this condition, try not to excite them too much, or else it can be an easy trigger for them. So the conclusion that I wanted to go through is different ion channels have different purposes, and of course different ions have different channels. You're not going to expect a potassium channel or a potassium ion to go through a chloride channel, and they're very specific. Of course, they are centered around different sizes and charges. So that is very specified for who they are, and so there is less of a problem of them, accidentally a potassium went through this channel. It's extremely unlikely and would show a deeper problem. They are triggered by different things. This can be the mechano triggers, the ligand. Some of them are open, and then of course voltage ones, depending on the gradient, what the gradients are allowing for the channels to open up for. Neurons need them to communicate. Cells need them to communicate with each other every so often. They're needed for muscular movement. They're needed for, again, biological processes. Your body needs them. Without them, you can't survive. You can't move around. You can't chew. You can't eat. You can't think. You can't feel pain. You can't feel anything. So they are extremely important. And then when things can go wrong, diseases can be very serious. And in super strong cases, they are very fatal. But in some of the ones like I showed today, it's just about kind of minimizing them. You can't change it. They're a mutation. There's not really a therapy that can go about it. But it's about finding what triggers them and not doing those, and living outside of those things to allow you to have a successful life. And of course, here are my references. Thank you.